Hey guys, I am going to discuss assignment 3 of calculus of variation. So now in the problem first, we need to prove that the shortest distance, the shortest distance between 2 points in the plane is a straight line. Or in other words, we can say that geodesic in the plane is a straight line. So first of all, I am going to clarify the new word coming in front of us, that is geodesic. So I am going to clear what is the geodesic, then I will give the whole proof of the given problem first. So I am going to clarify the word geodesic. Geodesic means that is the shortest, in other words we can say the shortest distance between 2 points on the surface. So in case if the surface is a plane, if the surface is plane, then let us draw the diagram. Let us suppose this is a plane, and I take the 2 points. Let us suppose that the point A, that is x1 comma y1, and point B, that is x2 comma y2. So shortest distance between the point A and B in the plane, that is a straight line. This is our shortest distance, a shortest length, or in terms this become a line. But if the surface is not a plane, mean like irregular surface, such type of surface, this is our surface. So now, but the surface is not a plane like a mountain. Let us suppose the surface is a mountain. So there will be different type of peak here, like that. So if I take a point here, that is a point, we can say that is a x1 comma y1, and let us suppose the point B, that is a x2 comma y2. Then shortest distance, shortest length between the point A and B, that will be a straight line. I know, you know also, but the shortest length will be like that. Shortest length will be this one. This will be our shortest length. Such type of length, we can say that is arc length. In other word, we can say that is arc length. So geodesic, in other word, geodesic, in other we can say the minimum arc length on any surface. So this is known as geodesic. So you will get wide information about geodesic in MSc. So now further, so now guys come to the point. Our in the problem first, we will give the whole proof. We need to prove that geodesic in the plane is a straight line. We have already discussed in the rough. So now, so first of all, we need to consider the let a point A, that is x1 comma y1, and the point B, that is x2 comma y2 are 2 points in the plane, and S is the arc length, or actually in the functional we need to minimize the arc length. S is the arc length of the curve AB. So now we will draw the diagram. So this is our required arc. So now we need to consider a point P and Q. Q is the neighboring point of P. Sorry, Q is the neighboring point of P. It will be that is the x plus dx, a small increment in x, and y plus dy, that is a small increment in y. Be at two adjacent points on a curve AB. So this point will be P, that is x comma y. This point will be Q, that is x plus dx, y plus dy. So now distance between the point PQ will be equal to the square root of, that is the coordinate x plus dx, negative x to whole square, plus y plus dy, negative y to whole square. So further simplifying, we will get that is square root of dx square plus that is dy square. So now further this PQ will be, that is the origin arc length, that is a small ds, and that is whole will be the arc from A to B, that is at S, and that will be ds. So now further ds will be equal to the square root of dx square plus dy square. Take the dx square common, then we will get 1 plus dy over dx to whole square multiplied to dx. And from here value of ds will be the square root of 1 plus y dash square dx. So this is our required ds. So now further on integration on both sides, on integration on both sides with respect to x, then we have total length will be s, will change from the initial point x1 to x2, and the square root of 1 plus y dash square dx. So from here this is our type of functional, that is the, so now here our functional f of x comma y dash will be equal to the square root of 1 plus y dash square with boundary condition. So these are boundary condition. So now we need to minimize the arc length s. So now here this is our given functional. So by using Euler differential equation, we have del f over del y negative d over dx of del f over del y dash is equal to 0. But this functional is independent of x and y, so this derivative will be 0, negative d over dx. So now differentiate the f with respect to y dash. It will give 1 upon 2 square root of 1 plus y dash square, and derivative of 1 plus y dash square, that is 2 times of y dash square, is equal to 0. So now further here 2 get cancel out, and it will give d over dx of y dash square over square root of 1 plus y dash square is equal to 0. So now on integration on both sides, we will get y dash over 1 plus y dash square is equal to c as a constant of integration. So now further on a squaring on both sides, we will get c square, and further it will give y dash square over 1 plus y dash square is equal to c square. So now the reciprocal on both sides, take the reciprocal. So now it implies that 1 plus y dash square over y dash square is equal to 1 over c square. So it will give 1 upon y dash square plus 1 is equal to 1 upon c square. So now here it implies 1 upon y dash square is equal to 1 over c square negative 1. It will give y dash square 1 upon y dash square is equal to 1 negative c square upon c square, that is y dash square is equal to c square upon 1 negative c square. So this is our whole constant, so we can assume here that is a square. So on comparing on both sides, y dash is equal to a. Further integration we will give y of x is equal to ax plus b, and it represent the family of a straight line. But these lines satisfy two boundary condition. So it means y passes passes through the points x1, y1 and x2, y2. Then the equation of line will be y negative y1 is equal to y2 negative y1 over x2 negative x1 multiplied to x negative x1. So this is our required functional, and this is our required final answer, and it represent this straight line. So now in problem 2 we need to find the extremal of the given functional. First of all, Let us consider the given functional I of y of x is equal to integration from 1 to 2 x to the power of 3 dx upon y dash square, and with boundary condition is given as, that is, y of 1 is equal to 0 and y dash of 2 is equal to 3. So now here our the given functional f of x comma y dash is equal to x to the power of 3 over y dash square, and you can see it is independent of y. Independent of y, it means we can say del f derivative, partial derivative with respect to y, has to be 0. So now by using Euler differential equation, del f over del y negative d over dx of del f over del y dash is equal to 0. So now further substitute all the value here. This quantity will be 0, negative d over dx, and the given functional, that is del over del y dash, that is x cube over y dash whole square is equal to 0. Now further here with the 0, negative d over dx, that is del over del y dash, that is x cube y dash to the power negative 2 is equal to 0. So now differentiate with respect to y dash partially, it will give negative d over dx, that is x cube multiplied to negative 2, that is y to the power y dash to the whole power negative 3 is equal to 0. So now this will give, take the negative 2 outside, it will give positive 2 d over dx of x to the power of 3 multiplied to y to the power of y dash the whole power negative 3 is equal to 0. So now integration, taking the integration on both sides, it will give x to the power 3 y dash to the whole power negative 3 is equal to c as a constant. Then we will get x over y dash to the whole power 3 is equal to c. Now take the cube root on both sides. It will give x upon y dash is equal to capital C to the whole power 3. So now take the reciprocal on both sides. Then we have y dash over x is equal to 1 over c 1 over 3. So now further, this is constant. Let us suppose that is a. So now here y dash will be equal to a times of x. So again integration on both sides, we will get y of x, integration of ax, that is a x square over 2 plus b as a constant, where a and b are arbitrary constants. So now we will use our boundary condition, and that is, and our boundary condition is, that is y of 1 is equal to 0. So by using that, a by 2 multiplied to 1 square plus b is equal to 0. So from here we will get a by 2 plus b is equal to 0. So let us suppose that is equation number 1. Further use the second condition, y of 2 is equal to 3. Then we have a by 2 multiplied to 2 square plus b is equal to 3. So now from here 2 to get cancel out. 2 times of a plus b is equal to 3. That is equation number 2. So now from 1, value of b, that is negative a by 2. So put this value in equation 2. So now put the value of b, that is negative a by 2, in equation 2. Then we will get 2 times of a, negative a by 2 is equal to 3. So we will get 3a over 2 is equal to 3. 3 get cancel out. So now here value of a is equal to 2. So put the value of a here to find the value of b. So then the value of b is equal to negative 2 by 2, that is a negative 1. So therefore we will get the value of a, that is a is equal to 2, and value of b, that is a negative 1. So our extremal will be, that is y of x is equal to, that is a square by 2 x square, that is 2 by 2 x square negative 1. So therefore our required extremal will be x square negative 1, and this is our required final answer. Now in the problem 4, so we need to find the extremal, of the given functional I. So first of all, let us consider the given functional I of y of x is equal to alpha to beta in bracket x y dash plus 1 multiplied to e to the power of x plus x square negative y dash dx, and with boundary condition is given as, that is y of alpha is equal to a and y of beta is equal to b. First of all, here our given functional f of x comma y dash is equal to x y dash plus 1 multiplied to e to the power of x plus x square negative y into y dash. As we can say that the given functional f depends on x, y and y dash. So we will use Euler, sorry, Euler's differential equation. So we can write here by using Euler differential equation, that is del f over del y negative d over dx of del f over del y dash is equal to 0. So first of all, we need to differentiate this functional with respect to y and with respect to y dash. So now differentiate the f with respect to y, then we will get, so here in this term you can see here this term is independent of y. So the whole term will be 0 plus x square becomes 0 negative, here is the y, So differentiate this term with respect to y, we will get negative y dash, negative d over dx. Differentiate the functional f with respect to y dash. So from here you can see that in this term, this is a depends on a y dash, independent of y dash, and here is y dash. So difference the whole term with respect to y dash, we will get a to the power of x, take outside, then here will be x multiplied to 1 plus 0 plus 0 negative difference with respect to y dash, it will give y is equal to 0. So now further simplifying, we will get negative y dash, negative d over dx. Here will be x time of e to the power of x negative y dash is equal to 0. So now find, again differentiate, open the bracket by differentiating with respect to x. So differentiate this whole term with respect to x, then we will get, apply the product rule, here will be that is a 1 e to the power of x plus x e to the power of x negative y double dash. So now uh, here will be y only, because that is a y, so here will be y only. So we will get here that is a y dash is equal to 0. So now further simplifying, we will get negative y dash, negative, that is 1 plus x e to the power of x negative y dash is equal to 0. So now open the bracket, multiply the whole term by negative, that is negative e to the power of x 1 plus x positive y dash is equal to 0. Here negative y dash, positive y dash get cancel out. So further here it will give e to the power of x multiply to 1 plus x is equal to 0. So you can see e to the power of x is always non-zero quantity. So that is, we will get x is equal to negative 1. But it is a line. It is a vertical line, not a curve. It is a vertical line, not a curve. Because extremal is expressed in terms of curve, that is y is equal to y of x, but it is not a y is equal to y of x. So we can say that extremal does not exist. So this is a very quite, we can say this is a very quite final answer. So now in the problem 5, in the problem 5, so let us consider the given functional I of y of x is equal to negative 1 to 2 square root of 1 plus y dash whole square over yd with boundary condition, that is y of negative 1 is equal to 1 and y of 2 is equal to 4. So here we need to find the extremal of the given functional. So as you can see here, the given functional, that is f of x comma y dash is equal to square root of 1 plus y dash whole square over y. So you can see that it is independent, it is independent of x. If it is independent of x, then we can say that del f over del x has to be 0. So now further, but as we know that Euler second form of differential equation, that is d over dx of f negative y dash del f over del y dash negative del f over del x is equal to 0. So here you can see del f over del x becomes 0. So by solving d over dx, substitute the f, that is square root of 1 plus y dash whole square over y negative y dash. Differentiate the given functional f with respect to y dash. So keep y 1 over y as outside and differentiate the square root of 1 plus y dash square with respect to y dash. It will give 1 upon 2 times of square root of 1 plus y dash whole square. Differentiate this term with respect to y dash. It will give 2 times of y dash. Here will be 0 is equal to 0. So further d over dx. So it will give the square root of 1 plus y dash whole square over y negative 2 get cancel out. It will give y dash whole square over y multiplied to the square root of 1 plus y dash whole square is equal to 0. So now d over dx. Simplify this bracket. Take the 1 over y or outside. Now cross multiply. So we will multiply the cross multiplication here, and if I take the y 1 upon y as a constant outside from the bracket, then we have to multiply the y dash square to 1. So it will give, that is a square root of 1 plus y dash whole square negative y dash square over square root of 1 plus y dash square is equal to 0. Further solving, we will get d over dx of 1 over y multiply to in bracket 1 plus y dash whole square negative y dash whole square over a square root of 1 plus y dash whole square is equal to 0. This part get cancelled out, and it will give d over dx of 1 over y times of square root of 1 plus y dash whole square is equal to 0. So now integrating on both sides, so it will give 1 upon y square root of 1 plus y dash whole square is equal to c as a constant of integration. So now squaring on both sides, we will get y square root of 1 plus y dash whole square. Squaring on both sides, it will give c square. So we can write here squaring on both sides. So it will give, that is 1 upon y square, and here it will give 1 plus y dash whole square is equal to c square. So taking the reciprocal on both sides, that is y square multiplied to 1 plus y dash whole square is equal to 1 upon c square. So that is 1 plus y dash whole square is equal to 1 upon y square c square. So it implies y dash whole square is equal to 1 upon y square multiplied to c square negative 1. So it will give 1 negative y square c square over y square c square. So now further take the square root on both sides. That is 1 negative y square c square over y square c square. So now divide the numerator and denominator by c square. It will give 1 upon c square negative y square over y square. So further it will give y dash is equal to square root of, we can write this term 1 upon c square as a square, because this is constant, negative y square and over, and it will give that is a y. So now further we can write here y dash, that is dy over dx, is equal to the square root of a square negative y square over y. So express in the variable separable form, that is y dy over square root of a square negative y square is equal to dx. So now further integrate on both sides plus b as a constant. Now substitute a square negative y square is equal to t. So on differentiation on both sides it will give 0 negative 2y dy is equal to dt. So now further y dy is equal to negative dt over 2. So further substitution it will give negative dt over 2 over square root of t is equal to integration of dx plus b, that is negative 1 by 2 the integration of dt over square root of t is equal to integration of dx plus b. So as we know that negative 1 over 2 integration 1 over root t, it will give 2 times of root t is equal to x plus b. 2 get cancel out, that is negative square root of t is equal to x plus b. So take the negative or multiply on both sides by negative sign, it will give square root of t is equal to negative x plus b, because multiplication of any constant by negative, again it become a constant. So we can express this term by capital B, that is we can write negative b is equal to capital B, and the value of t, that is a square negative y square is equal to negative x plus b. So now squaring on both sides it will give a square negative y square is equal to negative x plus b to whole square. So further we can write here, that is y square is equal to a square negative x plus b to whole square. And from here we can write value of y, that is square root of a square negative x plus b to whole square. So we will use by using the given boundary condition, and that is y of negative 1 is equal to 1 and y of 2 is equal to 4. So y of negative 1 is equal to 1. So by using here, that is 1, that is square root of a square negative that is 1 plus capital B to whole square. So it will give, that is a square negative 1 plus b to whole square is equal to 1. That is equation number 1. And second, it is given that y of 2 is equal to 4. It will give 4 and replace the x by 2, that is a square negative 2 plus b to whole square. Squaring on both sides, it will give 16 is equal to a square negative 2 plus b to whole square, and that is equation number 2. So subtract the equation 2 from 1. It implies a square negative 1 plus b to whole square negative a square negative of negative 2 plus b to whole square is equal to 1 negative 16. So here will be a square. Here a square get cancel out. So further negative times of 1 plus b square positive negative 2 plus capital B to whole square equal negative 15. So further simplifying, it will give negative 1 plus 2 times of b plus b square plus 4 negative 4b plus b square is equal to negative 15. Here we will negative 1 negative 2 times of b negative b square plus 4 negative 4b plus b square is equal to negative 15. B square get cancel out, and that is negative 2b negative 4, that negative 6b. Here will be plus 3 is equal to negative 15, that is negative 6b is equal to negative 18. So from here value of b is equal to 3. So now put the value of b in any first and second equation. So put this value of b in first equation, either in first or 2. I am going to put the value of b in the equation 1. So it will give, that is a square negative 1 plus b, that is 3 whole square is equal to 1. So that is value of a square is equal to 1 plus 16. It will give, that is 17. So now put the value of a square, put the value of a square and value of b is equal to 3 in the given extremal. So our extremal will be, that is y is equal to square root of a square, that is 17 negative of x plus 3 to whole square. Now open the bracket, we will give 17 negative x square negative 6x plus 9. So further simplifying, it will give 17 negative x square plus 6x negative 9, and 17 negative 9, that is 8 negative x square plus 6x. So therefore the required extremal is, that is y of x is equal to square root of, we can write in the standard form, that is 8 plus 6x negative x square, and this is our required final answer.